Alright, hello everyone. Welcome to the next calculus video. This is Professor Brian. What we're going to take a look at in this section are sometimes called solids of revolution or volume. Right? So we're going to consider finding the volume of rotating a specific area given within a region. So I'm going to call this volumes of revolution. And usually in most calculus books you look at two different techniques, and the one we're going to look at for now is what we call the disk or washer method. Now, it's a little difficult to sketch these volumes of rotation. So first of all, I'm going to do my best to sketch, and then there's a cool little applet I'm going to bring up that we can take a look at to kind of estimate or at least visualize what the volume is going to look like. So real quick, let's say that we're looking at, in particular, the area. Let's do this. Let's look at a specific example. So let's suppose we have the curve y equals x, and let's suppose we have the curve y equals root x. And we're looking at the area bounded between those curves right here. Right? So what we are going to do in particular, just like we were talking about in the last video, we're going to consider, let's say, the area between one of the rectangles, and we're going to rotate that. Let's say we're going to rotate for this conversation around the x-axis. So if we rotate that around the x-axis, think about what's going to happen here. We're going to have this region rotate. We're going to, essence, end up with this. And going to create a volume of rotation here. Right? So, you know, my figure might look something like, go away. My figure might look roughly something like this, right? And again, I'm going to do a bad job here, but we have a solid of revolution when we do that. That is not the best drawing, right? So here's my x-axis, let's say. Right? So in essence, this one particular rectangle will sketch the volume for this particular piece here. Now if I take that rectangle and I rotate around, what we're going to basically end up with is like a washer. So we're going to end up with that rectangle rotating a washer. I don't know why that keeps popping up, right? So we have an area between a curve, if you will, and that rotates and that creates kind of like a donut. Right? Now, the delta x of this rectangle is actually going to create thickness. Ooh, that kind of came out okay. It looks a little funny. So if you think about the volume of that one washer, what we have really is a surface area times a thickness. So the volume of that particular washer is the surface area times the thickness of that disc or that washer. Now in this particular case, if you look at that surface area, the surface area is the area of a circle. Well, technically it's the area of two circles, right? So we have the area of the outer circle, and we're going to subtract the area of the inner circle. So we're going to have like area, the surface, let me say the surface area, right, is going to be pi r squared. I'm going to call this the outer radius squared minus pi, and I have the inner radius squared. So again, if we look at this picture here, the outer radius comes up to the upper curve, and that's what creates this outer circle. And then this inner radius to the lower curve, right, is going to be right here, and that's what creates that guy. So we're going to want to subtract those two to create our volume. Now that's the surface area. So how do we create the volume of that, right? The thickness is the delta x. So again, the thickness here, my delta x is the thickness of my disk here, right? So my thickness is the delta x. So, you know, again, the beauty of Calc 1, we learned about the limit process, right? So again, the volume of the region rotated is approximated by the area, right? We have the area times the thickness, right, of each disk, right? And we're going to sum those up. We're going to have, let's say, n disks that we create. So I'm going to say, you know, the area of the ith disk, right, and the thickness of the ith disk, right? Now, you're not going to see that in a calculus book, right? So usually what you're going to see in a calculus book is something like this. They're going to say the area at some particular x value, and then the delta x at that particular x value. Right? So we're going to have n of those rectangles. And again, I'm going to sketch this particular example, right? So for this particular x value, we have some delta x, and then we have the area between the curves, right? So we have the outer radius and the inner radius. So for the disk washer, right, keep in mind for the disk washer, right, this is, you know, pi r outer squared, right? That's the area of the bigger circle, and then pi r inner squared, right? And, you know, our delta x, let's say, right? Right, so again, let me go ahead and squeeze that in here, right? What we're going to really do is the exact volume is going to be the limit as n goes to infinity of the n pieces of area that we rotate. So we're going to have n disks that we rotate here, right? So we're going to have n slices of rectangle that rotate. They're going to create a washer in that case. And remember, some books say this is delta x going to 0. So there's our Riemann sum that we have from that beautiful limit process, and that gives us the integral, right? So again, you know, I'm going to write it this way. This is how I personally prefer to think about it, right? R outer and R inner. To me, this makes more sense, right? But sometimes what you're going to see in a textbook, this thing has a mind of its own. Sometimes what you're going to see in a textbook is a scenario like this, right? So kind of like our example where we had here, we had y equals root x, right? So we would have, in our example, pi, we have root x squared minus pi times x squared. Right? And again, just to point out to you that when we look at this particular rectangle, right, the outer radius is the distance to the root function. The inner radius is the distance to y equals x. So that when we rotate that, we get that donut. Now again, for this particular example, my points of intersection are 0 to 1, so I would integrate from 0 to 1. So there was a quick, rough, dirty conversation with an example of what this would look like, or the concept of a volume of rotation. And we're going to come back to this in a second. I want to bring up this applet. Now, first of all, let me come back. In our example, we rotated around the x-axis, right? We rotated that volume around the x-axis. Sorry, we rotated that area around the x-axis to create volume. Now, in this scenario, they're taking this area right here and they're rotating around the y-axis. So first, let's just take a look at what that would look like. So if I rotate around the y-axis, we can see that that region rotates and generates a three-dimensional solid. And we are looking to calculate the volume of that three-dimensional solid. Now, if I rotate the entire area, right, and again, I'm looking at the area between these curves. If I rotate around the y-axis, that area rotates, gives me a three-dimensional volume. Now, let me look at just the approximating disk. So this is like our picture that we drew. Let me bring that back up. This is like our picture that we drew, and we were finding the area right here between the two curves, and we were rotating the area between the curves. Now, if you look at this, the difference between the curves really is this function and the y-axis, right? So there's the area that's getting rotated. And when I rotate that, you can see in this case we get what we would call a disk. There's no hole in the middle. So we would get a disk there as we rotate that. Now, Now, again, visually speaking, we're getting a surface area, which is a circle, a pi r squared, and then the thickness of the disk. Now, again, I don't mean to confuse you. In this case, the thickness of the disk is a vertical delta y, right? But in our picture, the way we drew it, it was a horizontal delta x. That was the thickness of my disk that I drew here. Oh, that was bad. All right. I love this visualization, though. It makes it so much easier to see. Right? So again, here's a rectangle that rotates and creates a disk, right? No hole in the middle, so no washer. So again, pi r squared times the thickness would give us that volume. Right? Now, for the scenario I created, I had area between curves. So we had the area of the outer circle minus the area of the inner circle, giving us the surface area of that washer, right, with the hole in the middle, the donut. So this is what we would call the disk washer method. Quick, dirty conversation here. Now, one thing I want to point out to you is how the disk or washer is created. The disk or washer is created by taking my slice of area, and that slice of area is perpendicular to the axis of rotation. So we were rotating around the x-axis. We drew our rectangle perpendicular to that. If we look at this scenario, they were rotating about the y-axis. Here's my y-axis. They drew their rectangle perpendicular to that. And that's what creates the circular disk or washer. So, crucial for us to think about that, because when we do the next section, we're going to actually create the rectangle in a different manner, right? So let's just make a note for ourselves here, all right, that the disk, or in some cases the washer, if it's area between the curves, is created by slicing the rectangle of area. Say by slicing the rectangles of area perpendicular. That's crucial. Perpendicular. Rectangles of area. Holy cow. Right? So we're going to slice the rectangles of area perpendicular to the axis of rotation. All right, and that is how the disk washer is generated, visually speaking. Now, let's come back to actually let's create a different example. Let's come back and look visually at what we drew initially, right? So again, we were looking at this area between the curves right here. We were looking at the area between root x and y equals x. And so we were rotating around the x-axis. So we took our rectangle and we drew it perpendicular to our axis of rotation. And when we rotate that, again, it creates a disk or a washer. Now, because we have a particular area between curves, right, that disk or washer, that disk has a middle to it, right? And the disk has a middle to it. And that's what creates the washer. All right, let's take a look at a different example. Now, again, I want to point out to you that technically I would need to evaluate this integral, right? Let's finish that off, all right? So if I'm going to evaluate this integral for this example, I'm going to have root x squared, which is just x, and I'm going to have x squared. And I'm going to go ahead and factor the pi out, all right? So I have a pi that's going to come out. Let's finish this example. I have a pi that's going to come out, and the root x squared is x, and then I get x squared dx. And we had 0 to 1 were our limits of integration. So, this would be what? We'd have 1/2 x squared minus 1/3 x cubed, and we'd go 0 to pi. Excuse me, I got pi on the brain because I'm hungry. This would be 0 to 1 as my limits of integration. Right? cherry pie. That's my favorite. What's your favorite pie? Cherry pie's so good. Apple pie's good too. All right, so we have pi, and then, when I plug the 1 in, I'm going to get 1 squared and 1 cubed. So this is 1/2 minus 1/3. And then minus pi times, oh, well, look, when I plug 0 in, it's all just one big 0. So what do I have in this case? Let's see, 1/2 minus 1/3, multiply, common denominator 6, multiply by 3, so I get 3/6 minus 2/6, so that's 1/6 pi. Now, let me point out to you, in this case, we're talking about volume, so that's going to be cubic units. Right? All right, why is that cubic units? Again, back up here in our conceptual conversation that we were having, we were talking about the area, we're talking about the volume comes from that washer or disc, right? So when we look at this washer or disc, we had a surface area. So this was the surface area. And keep in mind, surface area is square units. And then the thickness of this disc, which creates the volume, right? That's a unit of delta x. The thickness is, let's say, inches times inches squared is going to give me cubic inches. So we're always going to be creating a volume of cubic inches, or cubic units, whatever my units are. All right, let's take a look at a slightly different example in this scenario. And let's come back to what that visualization was on that simulation that we looked at, right? That applet. Right? So in this case, let's consider that we have the region. I'm going to take a look at an example here. Let's say we have the region bounded by x equals 2 root of y. So we have the region bounded by x equals 2 root of y. And then we want to look at between the x equals 0, y equals 9, and the y-axis. X equals 0, y equals 9. And we're going to rotate about the y-axis. Okay, so let's visualize this scenario that we have here. Okay. All right, so we want to take a look at x equals 2 root y. All right, now if we think about this for a second, let's suppose the 2 isn't there. We have x equals root y, or y equals x squared. So we really have y equals x squared, right? But we only have the positive portion because we have the positive root. So, the 2 would stretch it vertically, well, horizontally in this case, because we're stretching the x. Right? And then we have x equals 0, which is the y-axis, and then y equals 9. So here's y equals 9. So we're looking at this region here, and we're going to rotate that around the y-axis. Now, I'm going to draw a representative rectangle. So remember, disk washer, if this is my axis of rotation, disk washer is perpendicular to that axis of rotation. Now, I'm looking at the entire area here. So when I rotate that, go away. When I rotate all of that, right, it's a solid disk. There's no washer, there's no middle. Right? Now, again, keep in mind, I'm going to get a delta y that happens here. So the thickness of my rectangle, I'm using lots of color here, right? The thickness of my rectangle, my delta y, right, is what's going to create the thickness of this disk, right? That's what's creating the volume. Man, it is a horrible picture, all right? Hopefully you get the point there, visually speaking. So the dy is what we're going to look at, right? So we're going to have the, the area of the circle, and then the dy is the thickness. Right? Now in this case, the area of the circle, my radius for this circle is a horizontal x distance, right? It's a horizontal x distance, and x is described as 2 root of y. So there's my horizontal radius. Now, one thing to keep in mind is that kind of the easy way to figure out what your variable of integration is what's the thickness of your rectangle, right? So again, here's my line of rotation, the y-axis. I cut perpendicular to that, so the thickness is a delta y. That tells me an entire integral needs to be in terms of y. That's my dy. So I have the area of my circle times its thickness. All right, so here's the setup of my integral. And then in this case, what are my y limits? Right, keep in mind I'm going to have rectangles. All of these rectangles are going to live between y equals 0 and 9. So my y limits of integration are 0 to 9. They would be the setup of my integral. Now, I'm not going to go through working out that integral. I'm going to assume you can handle that. But there's the setup of my integral. So whatever I would get out of that antiderivative, that would be the volume for rotating the region bounded by these three curves about the y-axis. All right, let's take a look at one last example here. So for these three examples, I've provided the picture, and I'm just saying let's set up the integral, right? Again, this is the new aspect of these problems, is setting these integrals up. Evaluating the integrals is technically something you've done prior, so I don't want to focus on that anymore. So all three of these are using disk washer method. And the first one says we're going to rotate the region about the x-axis. So here's the shaded region. We're going to rotate about the x-axis. So if we're rotating about the x-axis, we're going to slice a particular piece of area perpendicular to the axis of rotation. Now, if we think about the area caught between those curves, when we rotate that, right, for this problem, it's going to create an open hole, right? This open space of area creates that open hole. So I have an outer radius. My outer radius is to this line, which looks like the horizontal line y equals 2. And then the inner radius is to the bottom curve, right? So this is really like area between two curves, kind of like we talked about in the prior section, right? But I have the outer and the inner in terms of radius, right? So in my integral, I'm going to have pi times r squared, and it's the outer radius. So my outer radius is 2 squared, and then I have pi, and then the inner squared is the distance to this function. Now, I'm getting a little bit ahead of myself here, so let me slow down for a second. Keep in mind that the thickness of this rectangle is a delta x. So this is going to all be in terms of x. Right? I just wanted to point that out to myself real quick. So even though this isn't in terms of x, right, this one needs to be in terms of x. So when I look at this inner distance, right, it's this y vertical distance to the bottom curve. So here's that curve. So the y as a function of x would be x to the 3/2. Right? So square root both sides. That gives me a 1/2 exponent, and that's going to get squared. So there's the setup of that integral in terms of x because of us slicing perpendicular to the line of rotation. The thickness is a delta x. Everything has to be in terms of x. And in this case, we need the x limits of integration. So we can see 1.587 is that x limit, and 0 is the lower limit, 1.587. So there's the setup, rotating that region about the x-axis. Now, let's suppose we want to rotate that region around the line y equals -1. So, let me come back. Let's erase this because this is going to get cluttered. So I'm going to rotate about the line y equals -1. And let me switch to red. So if we think about this, here's the line y equals -1. So I'm going to cut my rectangle from that line, and it has to be perpendicular. So I'm going to cut the rectangle from that line, and it has to be perpendicular. And I'm still looking at the area between the curves that gets rotated. And again, that's going to create an open hole around the line y equals -1. It's going to create a disk washer. Now again, the thickness here is a delta x. So when I set up my integral, I'm still going to have a dx as my thickness. Now, when I think about the radius, right, the distance from here to here, I still have to go to the upper curve, but the distance of 2, y equals 2, is from the x-axis, and I have an extra unit of 1 down to -1 here. So I really have 1 plus 2, which is 3. So I really have, let me pull my pi out, right? I have pi times 3 squared. That's my outer radius. And then minus pi times what's my inner radius, right? Well, again, my inner radius is from here to the function. Now, we talked about in the prior example, if I solve for y, I get x to the 3 halves. Now, x to the 3 halves is this distance, and then I have to add 1 to that. So I'm going to have, I didn't give myself enough room, I'm going to have the x to the 3 halves, and I have to add 1 to that. There's my inner radius. Right? So there would be the setup. Oops. From 0 to 1.587. So if my line is parallel to my axis of rotation, I have to consider what is that doing to my radius. And in this case, it was adding 1 to each radius. Right, and then the last one says set up an integral, do not evaluate, to find the volume from rotating the region around the y-axis. So again, to avoid a bunch of cluttering here, let's draw that picture and let's do it in green. So I'm taking this region and I'm rotating about the y-axis. So because we're doing disk washer, here's my line of rotation. My rectangle must be perpendicular to that line of rotation. And again, I'm going to end up with a delta y for that integral. So I'm going to have, some integral dy. So everything has to be in terms of y. So when I think of the radii, let me pull the pi out. So from my line of rotation, the outer distance to the curve is the distance to the curve. So again, this is an x horizontal distance, right? So again, because I need everything in terms of y, then I have to come up here to my equation. I have to solve for x as a function of y. So I'm going to cube root both sides, and I'm going to get y to the 2/3 as my outer radius. So again, from the line of rotation to the outer portion of the region, that's my function x equals y to the 2/3. So that's my outer radius. Now my inner radius is right here. It's no distance from my line of rotation, right? Again, my line of rotation was the y-axis here, right? So the distance from the y-axis to the bottom of the region is 0. So technically, I didn't even need to write this at all. That's 0. And again, if you think about rotating this guy right here, it's going to be a solid disk. Right? It's going to be a solid disk. So here's my typical slice of area. There's no hole in that disk. It's not a washer. It's a solid disk. Now, I need y limits of integration. So my y limits go from 0 up to a y value of 2. So I'm going to put my y limits of 0 to 2. All right, so there's a conversation about volumes of rotation using the method of disk and washer.